Hello everyone. Welcome to this series of lectures on deep foundation models. So myself Sriram Ganapati, I will be discussing the foundation models part 1 today, which includes topics relevant to transformers, relevant to attention, and also how the pre-training and fine-tuning tasks of a transformer are developed. So this lecture is going to be subsequent to the previous lectures that you may have had on convolutional neural networks, on feed-forward neural networks, recurrent neural networks, and so forth. So it's going to add yet another set of models and more recent progress and updates in the field of sequence-to-sequence models. So today's lecture will talk more details of a transformer model, the subsequent lectures that will cover more of large language models and image based models based on diffusion. So let us get started. So what we are going to cover primarily today in this lecture series, right? I want to get a little bit of a scoping done at the front itself so that expectations are set, and some of you, if you are here for something else, you may want to take this slide into consideration, which is what we are going to cover and what we are not going to cover in this series of lectures, which is about 3 of them. So we'll try to cover a lot of the topics in terms of what are those methods, what are those techniques, how they have been, let us say, used, and so forth. But some amount of why those techniques are useful, why they were coming into place in the first hand, and also a little bit of where they are going to get applied. So a bit of aspects related to what, why, and some amount of where will be covered. But what we will not have time to go through in detail, largely because of the short span of these lectures, as well as due to the wide audience that we have, we will not have time to go into detailed mathematical foundations of this, detailed mathematical underpinning that has brought out some of these techniques. Some of the algorithmic details purely from a computational point of view, purely from an implementation point of view. So we will not have time to go into aspects that cover implementation related considerations of various models and architectures that we will be discussing in this, right? So with that little caveat, what we will try to do today is get to the topic directly on foundation models, right? So as many of us are users of various foundation models ourselves, right? They have become ubiquitous, and including this slide lecture series, I have generously used ChatGPT like tools. So why not start there itself? What ChatGPT or any GPT model thinks of itself, right? So a foundation model is a large class of models, and what does it quantify or qualify to call a model a foundation model, right? That's the first definition we want to start with. So these are large scale models, right? And they are trained with massive and diverse data sets, right? But that is not the reason to call them foundation models. The primary reason to call them foundation is because they become the bedrock, they become the starting point, they become the foundation to branch out various other modeling steps, architectures, tasks, applications, etc. Various other specialized tasks and applications can be built on top of this. So any model that you build in a large diverse scale, which has at least the scope to branch out to 2 or more tasks than it was originally designed for, then you can start coining the term foundation models. Obviously, these are not very strong or very mathematically precise definitions, right? You can think of deep learning. How do you want to quantify what is deep learning, right? Is it 1 layer or 2 layers on which you start calling a feed forward network as a deep learning model, or is it more than 2 layers? So there is no real solid, let us say, mathematical definition of this, but basically we start saying that more than 1 layer, then it starts acting as a deep model. In the same flavor and manner, models which are generalizable which can form the bedrock for more than 2 or more tasks that you can start off from them, would quantify as a foundation model, right? So it's not again that these foundation models are very new. They have been in existence. People have been, let's say, thinking of them even well before, let us say, the topics that we will consider today. But what has been, let us say, revolutionary in this is the coupling of deep learning, the coupling of transformers, which is going to be the key topic of today's discussion, and then the scale in which you can rapidly develop these foundation models. That has really revolutionized this particular area of AI, right? So the atomic units, right, the fundamental units that form the core of these foundation models, these are the transformers which we are going to discuss in the detailed aspects in the rest of the slides, right? So now if you ask for some examples, you can find large number of them that have been appearing, and most of them, let's say, at least in the deep foundation model world, using transformers, they have started coming up, propping up about 5 to 7 years ago, right? So we'll also talk a little bit of history. The other aspect about this set of talks and lectures is that I'll give pointers, I'll give paper citations and more details where one can follow up. So this is going to provide as some sort of again a basis to go detailed as and when you want to consider understanding them in more details, when you want to basically dwell deeper into how some of these came up, what is the positioning when they were proposed as papers at that time, and so forth, right? And last but not least, one more caveat is this is a very evolving field, and whatever we are discussing today is some sort of a snapshot, maybe a snapshot that is a few months even before that. Every month, every passing fortnight, there are some developments and new techniques that keep coming up in this field. Okay, so the contents of today's lecture, right? So today, in the rest of about 90 minutes or so, what we will try to focus on are these aspects. These are largely taken from the syllabus that I had put out in the call for this seminar series. So in particular, we'll talk about transformer architectures, primarily focusing on attention mechanism, which is one of the key new things. So assuming that most of you have had some exposure to deep learning in terms of convolutional neural networks or feed-forward neural networks, this is basically going to add more on top of it in terms of attention, in terms of in-context learning, low-rank adaptation, and later on we will start talking about objective functions that one should use to train these models. So let us start in this setting of a transformer model, and we will primarily focus on attention mechanism to start with. Right? Again, a little bit of the why that transformers came into place, we will start there. What was the context in which a transformers a proposal came up, and what is the context that has driven their success is also going to be part of our discussion. So the fundamental motivation, right, for many of it, in fact all of this lecture series as well as today's talk, is going to be attempts to model time series data, right? So a data which is of the form x of t, right, where x is some vector, matrix, tensor representation of a real world phenomenon, and t not necessarily has to be time but some index of ordering, right, some index where you can start seeing something which starts at some location and then it continues to evolve as a function of that variable, is going to be the form of data that is of interest for the transformer style models. So this x of t, in some of the starting simplifications and analysis, we will just assume that x is basically a vector and x of t therefore corresponds to a vector time series, right? So again, just to keep ourselves honest, t necessarily does not mean that it is time. It is just a index to order certain variables that we have ordered. So let's start with an example. Let's say many of us use wearables, right? So, and many of them, the ones that you wear can measure your heart rate. You click on your heart rate monitor and suddenly it can pick up some level of heart rate activity. So if this is some sort of a profile of your heart rate that you are measuring, now I can start forming a time series data out of this, right? Again, there are lots of design considerations or domain specific characteristics that I am omitting for the larger part in this presentation. But assume that you can form some sized reasonably sized windows in which you are going to apply some sort of a modeling or feature transformation. So this is what you see now as these kind of blocks or chunks, and the particular size, the particular shape of the window you want to apply, what is it that you know, the regularity or ordering of this time series, what frequently happens and so forth, is very domain specific. So in this case, maybe I have chosen something like 800 milliseconds or less than a second as one window of operation. For various other signals, if you take an audio, if you take a music, if you take images in the form of a visual content that is coming up through a video, you have different sort of sampling rates as well as different sorts of window of operation, right? So without delving deeper into the domain specific characteristics, assume that somebody has told us how to window these data points and derive some features, and say this is your vector that you have formed by representing this part of the signal, and now you have a series of such vectors that are evolving over time, right? So the question then is, now I also want to do some modeling on this, and in this particular exercise example, I am going to try to model some sort of normality or abnormality of the heart rate data. So specifically, as you see here with the highlight, certain portion or window is highlighting a irregular heart activity, and therefore maybe you have started with some expert, a human or a cardiologist in this case, to have looked at this heart rate signal and mentioned that this particular window of activity is not looking normal, right? So then you have a simple binary classification that you have to deal with, which is that for every window in time where which you have features, you also have the corresponding labels, right? And the label is a binary label. 0 corresponds to a normal heart activity and 1 corresponds to an abnormal heart activity, right? So now I have both data and labels, and now I want to conduct a model development phase which can use some of this expert annotated data, become a predictive mechanism using this expert annotated data to now be able to come up with a model that can eventually, let's say, become autonomous, right? So you want to add your sensor data, feed it to a model, and then the model constantly keeps monitoring, checking your heart activity, and then you may add additional logic on top of it. Maybe if there is abnormal activity for more than 10 seconds, maybe you give an alert. If you have more than 40 seconds or 50 seconds of abnormal activity, then you start making a phone call to an emergency number. So this sort of additional logic you can put to ensure more utility of this kind of monitors. So now from a modeling point of view, if I basically say that my task is to predict y of t given x of t, right? So the information that y3 in this case, based on the ordering that you are seeing here, the information that we want to capture through the modeling exercise is that the third time instant it started behaving abnormal, it may just not be only constrained to that window of analysis. The information could be spread over time, right? Something which we will eventually start calling as context, right? Anything that you are now going to predict or are going to have as a modeling task is not only influenced by what happens then and there, but is influenced by a set of events either before and in some cases set of events that happen after this phenomenon, right? So if I now ask the question, why can't we use let's say more conventional models, if I can use the term, like a deep neural network or a convolutional network that some of you may be familiar with, to directly take every instance, say an x of t, directly take it to y of t. So you do it for x1, then you do it for x2, then you do it for x3 and so forth. So then first thing that you already see is that by the time you have reached and started calling something, the event has already occurred, right? It is not predictive anymore. It has already occurred that you already have at least one instance of a abnormal heart activity. More importantly, as you see here, the second instance itself, the window at the second instance, which is a different highlighting in the slide, is already starting to indicate that things are moving in the wrong direction, right? So the PQRS wave is essentially the PQRST wave is essentially the technical term for this sort of a heart activity pattern. So what you start seeing is already there is some indicator from the instance at time 2 that things are becoming abnormal, and now you want to use not just that particular instance but also the neighborhood, the context that we define to make improved decisions. So building then on top of this simple enough motivation, we want to basically say, I don't want to treat each instance as an independent occurrence of certain physical or real world event. I want to now treat it as a collection, as an array, as a sequence, right? So we want to treat inputs as sequences, and in cases like what we discussed just now, we also want to keep outputs as sequences, right? So the input is evolving over time, output is evolving over time, and now the fundamental goal then becomes, I want to put a model at this particular space where you can take the input as a sequence and attempt to provide a model that sits in between the mapping of the sequence to the sequence. So if you ask then, compared to a CNN or DNN in one line, what is the advantage you get? The advantage you get is modeling dependency across the sequence. The sequence has information spread across multiple time events, and without capturing this, you may still be able to conduct a model, but a more realistic, more signal, let's say informed model, right, would be to try to look at the evolution, the pattern that is evolving in time, and try to attempt the modeling of the dependencies across time events, right? Again, the term time is loosely used here. It can also mean any form of ordering. So this is a dense slide. So let us slowly start breaking it into parts that we want to talk about. So for example, the first mention I want to do is there are several methods, right? Now whatever we are going to talk about in detail is one of those model architectures that propped up, but we also need to be aware of the context, the history in which this particular model appeared when it was proposed, right? So when about 2018 or so, in which we are going to deep dive into transformers as models, when about 2018 these transformer models were proposed, at that time the popular architecture to perform sequence modeling is what is called an RNN, right? A recurrent neural network. We will not go detailed into an RNN, except to say that the fundamental principle in which an RNN operates is to model a one-step dependency. Meaning at every instance in time, you try to look at one instance before. So it becomes like a recurrent, it becomes like a recursive use of the previous time instance. The previous time instance becomes dependent on the instance before that, the one before that depends on the one further before that, and it forms a chain of dependency that can in principle attempt to model a reasonably long term dependency. So by creating this one step in a statistical world, any one step probabilistic dependencies are called Markovian. So a one step dependency kind of approach applied to a neural network architecture is what results in an RNN, right? But even when these models were becoming very popular, very heavily used, if you ask language models in text, if you ask acoustic models in speech, if you ask video models that look at video as sequence of data points, everybody, even at 2018-17 when transformers, which I am going to talk about in detail, people were already aware of the deficiencies of an RNN, which is that it has this one step dependency, which is that you cannot see directly anything more than one step, right? Indirectly, implicitly they all contribute, but explicitly you are forcing the model to only have one step dependency. And even with the one step dependency, the computational, right, and other aspects were already significant. People were aware of these kind of deficiencies, but there were not enough compelling arguments for newer architectures, right? There were not enough compelling candidates as newer architectures that could propel the field. And you could start arguing in some sense, this is also reflected today, which is that we also know certain issues and deficiencies of transformer models. While I have not discussed that just yet, but we will also talk potentially a little bit about it. There is also not a real compelling candidate that can replace, right? People are talking about it. Maybe some of you have listened to recent discussions by Yann LeCun and others about need for alternate world like models than transformers, but there are certainly not equally compelling candidates thus far. But coming back to the RNN, the other issue that was significantly, already in awareness, already in the world, the developers' knowledge of these models was these suffered from vanishing gradients, meaning while these models in principle can attempt to model a very long time dependency, in practice they had what is called a fading memory. They had what is in the psychology world what they call as recency bias, right? We humans also have it. We tend to remember a lot more about what happened today morning than last Friday and so forth. So same thing in modeling world, there was a significant drop as and when the memory, as and when the dependency context was increased, there was a consistent drop in the dependency possible. So how can one measure this? For example, you can start saying that if I have a sequence of length 50, if I have a sequence of length 50 and then I start looking at the output at say 40th instance and start measuring what is the gradient of that output with respect to an input at say instance 5, right? So now when you start looking at the gradients, it starts telling you how much influence any sample has on the output. So a change in x of 5, how does it affect a y at 40? And when you start seeing those to be very low, right, because of the model weights, because of the one step recurrence, then you start knowing that even if I change my input significantly at the instance 5, its effect on the output at 40 is almost negligible, right? So this was aware at that time, but there weren't alternatives. There weren't other alternatives, right? So the fundamental question then is, which motivated the topic that we are going to discuss today is, can we do the modeling as a, irrespective of the one-step memory, as a full blown so-called attention over all the previous time steps, right? So we are going to spend a good amount of time on one of these landmark papers in this field. This came in NeurIPS 2017, sorry, almost about 8 years ago, and has kind of revolutionized, changed the way things have moved, right? So deep learning to convolutions, maybe you can call it as one splash of change, particularly for the visual world or the image world. And if you ask then, from convolutions and recurrence to a transformer, has fundamentally changed natural language processing, and then further influenced various other domains, including audio, music, speech, then images and video signals, biomedical data, and so forth. And if you look at, let us say, when I was preparing these slides about a few days ago, this particular paper alone has about 200,000 plus citations, right? About 2 lakh citations for just a single paper. I don't think it has been matched by any other work, to my best of my knowledge, right? So that has been the change that this particular work brought to the field. So in many of these discussions, what I will try to do is, I will try to paint a big picture. What are we going to cover? Then we will try to piece these things apart and then put it all together, so that the big picture again evolves through the set of slides. Right, so the big picture in this case is the focus on what we call as attend, right? Every input tries to attend, tries to become dependent, or tries to influence every other input representation, including itself, right? And then you are going to evolve this in a deep framework. So the deep learning world before this and even after this is basically a mechanism in which, if you build a concept, you can keep doing it in a sequence of similar steps and improve the advantage of each of these modeling or transformation steps. So when it comes to applying to transformers, if you know how to do an attention, if you know how to do a way in which you can model every input as a function of every other input in one processing step, you can repeat this in a deep fashion and make it a deep transformer style model. So the other aspect is to have these representations evolve into subsequent layers. They are going to be dependent on the similarity, right? The dot product, which we will talk about, the similarity between a representation and its other temporal neighbors. And to build this processing, the paper that we are discussing put together attention, some level of other aspects like residual connection, like normalization, feed forward layers, positional encoding. I will touch upon briefly most of the other things, but if you ask me, even when the paper proposed it, the attention was the new kid in the block, right? The attention was largely the unknown aspect that this paper brought to the field. So let us then again, following the notion we did in the first part of the heart rate and heartbeat monitoring, let's try to now also piece together all these building blocks through an example, right? So suppose I have a text case. In this case, I'm going to significantly rely on text as the modality to bring together the components of a transformer. So let us say I have a sentence of this nature saying, I am a student of machine learning, and assume that some way exists which we are not going to deal with in this lectures, which is to convert these words into some fixed dimensional vector representations, right? So there are prior models, if you want pointers, like word to vec, kind of embeddings, hash maps of text, and various other prior works have led to converting pieces of text to vector representations. But for our discussion, assume that your sentence, which consists of in this case 7 words, right, each word is a vector. Right? Now you have a sequence of 7 words in a particular order, and this is what I am going to call as xt, right, and note that I am notating all of them as some sort of row vectors, which becomes useful to consider in terms of the dimensions, right. So about 7 vectors in time have come. Now what do I mean by this so called similarity or so called dot product, so called cross correlation? If you ask a signal processing engineer, they will start calling it cross correlations. So suppose I have every vector in a vector dimensional space, right. One way of measuring similarity between 2 vectors is to form a dot product between them, right. So if I take x1 as a row vector, now I can find pairwise similarity between that vector and every other vector in the sequence, right. So have x1, x1 transpose, and now you can form the whole set of pairwise similarity between pairs of vectors. What do we end up with? Now if I have 7 instances, I could come up with a 7 cross 7 matrix, right. Every vector associates or connects with every other vector including itself, and of course this becomes a symmetric, this becomes has other properties of what correlation matrices have and so forth. It becomes a positive semi-definite matrix and so forth. But for the sake of our discussion, what you now have is a matrix with elements being each scalar consisting of some sort of a similarity, some sort of an association between a pair of I and j vectors, right. So if I can start calling this matrix as A, right, I am going to call this matrix as A. What I can then start thinking of is, so this one now starts measuring x1 with x1, this starts measuring with x1 with x2, and this starts measuring with x1 with x3 and so forth. So now can I now start, when I start doing something like this, right, if I take this matrix A and multiply with a set of row vectors, right, x, what you are actually doing is, when I want to, let us say, contribute all of this, let us say, starts becoming your new x1 hat, right. So when I want to basically start making the new vector or the subsequent vector, or I should call it E1 hat, this whole set of rows, right. So what is now happening in this series of scalars is it becomes a weight, right. So if I take, let us say, this component, this becomes a sort of weight to tell that x1 is also this much dependent on x2, right. So when I want to form the new embedding post the transformation, I want to add to x1 some portion of x2 as well, and how much portion of x2 is going to be decided by this similarity between 1 and 2, right. So if I now start building the next embedding, it is going to have some dependency, some portion of x2 also coming in, some portion of x3 also coming in. So here you would have x1, x3 transpose. So this is going to tell us how much of x3 has to be added to, let us say, the next embedding at time instance 1 to cover for the subsequent embedding, right. So weigh every vector, so that is what the first line here says. So weigh every vector with weights derived from the cross correlation. So if I do this, whatever I said just now, you can keep doing it, but there isn't any learnable component, there isn't any transformation happening, right. Remember that part of the motivation to call these models transformers is because they transform the data, right, they apply some transformations on the data. So the subsequent, let us say, process is to apply transformations to essentially take, right, every input data and pass it through 3 levels of transformations, one corresponding to query, key and value. Again, these terms come from text mining and data mining fields. But if you see from our previous slide and discussion, what this would mean is that I have 3 versions of the data, 3 transformed representations or versions of the data, each with some learnable set of matrices W, Q, W, K and W, V. So with these 3 versions or copies of the data, then you can start forming pairwise similarity between a query and a key, pairs, all sorts of pairs, and then you start getting elements of the form Q1 K1 transpose, Q1 K2 transpose and so forth, and now you have a whole 7 cross 7 or a sequence of such entries, each carrying again similarity values but on the transformed outputs. So this, whatever you see here, which is in a matrix form A equal to Q times K transpose, in this field is called the dot product, right, the dot product attention. It captures the pairwise relationships of transformed vectors. Now you can ask, what do we do with this, right? So what I am going to do with this is basically take all these, apply a normalization. So in this case a softmax of A by D, D is basically the dimension, it's a scalar, so you divide by the dimension to have some sort of stability for the softmax that you apply, so that if you have more dimensions you will do a larger scalar value to divide. So primarily a scalar or a temperature, if you want to call it in terms of the softmax use. You apply that on the rows of the matrix A and then perform a softmax, so that this then becomes a set of numbers which are all normalized and summed to 1, and they become the weights in which you will apply to the row vectors of the value matrix V, right. So let us see a more a stronger example of this applied to this, and I will also show some numerical values to further elucidate this. So if we take this example of I am a student of machine learning and I am start looking at pairwise relationships, so Q1 K1 transpose, Q1 K2 transpose and so forth, obviously certain numbers, right, certain dot product values tend to be higher, right, and when you apply the softmax they tend to get further accentuated. And now as you can see, maybe the word I is much more strongly connected to word I itself as well as the word student, right. Again, this is not enforced or this is not applied as a rule, this is what you expect the model to learn from the data, that what associations are important to be learned, what associations need to be emphasized and what associations need to be de-emphasized, right. So the fundamental then processing step that moves this is enriching connections which are closely related and using that as a weight to subsequently improve your embeddings or representations, right. So if you want to take a real numerical approach to this operation, so suppose you have queries which are these row vectors Q1 to Q7, keys also which are row vectors of Q1 to Q7, all for the sentence I am a student of machine learning. Now when you start applying this so called dot product attention, let us say you get values like 14, like 3 and so forth, and some values are going to be high, some values are going to be negative and low and so forth. And finally when you apply softmax on it, as you can start seeing, you get something like 0.6, 0.2, 0.09 etc. as values. So what would this mean, right? So this, in this case it means for the word, let us say student, and if you are looking at Q4 as your query, right, the fourth instance as your anchor point to look at. For the fourth instance of student, the rest of the words in the sentence that matter most are being I, machine learning, etc. are the significant parts. And then if you look at the other function words like of, am, etc., they are less relevant. So what we are going to do now is to take about 0.2 of I, 0.6 of student itself, and then 0.09 of machine and 0.03 of learning, and now you add all of it with those weights, the value vectors for all of these instances, and that is what is going to become the embedding for the location at student in the output of the attention, right. So a similarity based approach that you get can expand to a transformed data, can make learnable weights out of this, and can perform sequentially on the data. So continuing this journey in the next setting. Thank you.